All right, guys. So obviously not here today. So I'm going to go through some of the questions, the same ones that I went through with the other classes. So we're doing two packets today, number and quantity and statistics. So for the number and quantity, you may have seen this question. It was on the practice MCAS. So we'll just kind of go over it. But basically, if any part of an expression has an irrational part, it's very likely that the whole thing is going to be irrational. Um, in this case, right, irrational is really, we're talking about pi, repeating decimals with no pattern. So pi is an example like that, and then any non-perfect radicals are going to be irrational, right? So like root 9 is a perfect radical. That's the same thing as 3. So this is really 3 times 3, which is 9. But root 2 is not a perfect radical. So that means this whole thing would be irrational, right? Because if one part's irrational, it kind of contaminates the whole thing, and now the whole thing's irrational. Same thing with the second one here. So root 9 again is 3, but if it's over pi, that means there's an irrational part, so the whole thing is going to be irrational. The third one is definitely a little bit trickier, right? With the third one, this is like kind of where, some kids might get exceeding, would probably get this one, but I still think you can get it if you just take your time and kind of go through it, right? It has the square root of pi squared. So the square root of pi squared is just pi. So you get a pi on top and you have a pi on bottom. So that would basically cancel out because square root of pi squared is just pi. So those pi's canceled out. And then root 24 over root 6 is, you can combine it under one root. That's the square root of 4, which, believe it or not, the square root of 4, even though it's a square root, it's perfect, it equals 2. So that answer, after all that, what it looked like actually ended up being rational, right? These first two were still irrational. And then the last one, again, you have a irrational part. It's never going to be made rational like it was in this one here. So that whole thing is just going to be irrational, right? And it's similar for part B. Same thing, you have an irrational part. This is rational. I know it's a decimal, but it doesn't repeat in some random pattern forever, right? Like 1.66666, that is rational because it's a pattern. This one just stops at 1.8. So you can write as a ratio, 18/10 if you wanted to. But this part, you cannot write as a ratio, right? That's irrational because of the radical. So that means this whole expression is irrational because one of the terms is irrational, right? So it kind of contaminates the whole thing in there as well. And again, when you see radicals and exponents, what you need to remember is ID. This is going to come up, and I know we've done it a few times this year. You've got to remember that the index is the denominator. So in this case, the index is 3, so it's t to the power of, and like it has like a 1 on the t. You don't see an exponent there, but it's like a 1 essentially. So it's t to the power of 1/3. It's the same thing as the third root of t. So obviously that one works. That's the same exact thing as the third root of t. Obviously it's not t to the 2/3 or 3/2. That's not the same thing as 1/3. And the rest of these is just your exponent rules, right? If you have the same base over the same base, your rule for exponents is that you subtract them, right? So like x to the 5th over x to the 2nd, that's x to the 5 minus 2, which is x to the 3rd. Same thing as x times x times x times x times x over x to the 2nd is 2 of them. So you cancel out 2, you just get 3 left. So the rule for these 3 is basically you would subtract them, right? So, 1/3 minus 2/3 would give you negative 1/3, which is not the same as positive 1/3. So that's not it. The fact that it says there's 3 of them probably means the next 2 are good, but it is, right? So 2/3 minus 1/3 is 1/3, so t to the 1/3, that's good. And then 4/3 minus 1, same thing as 4/3 minus 3/3 is 1/3 as well, so you get t to the 1/3 that way as well. So the first one and the last two are good. All right, next one here, we're going to go to number 3, right? So number 3, 10 years ago. Now this question, is not on the calculator section. And you're like, well, 5,085, 19.51. This is closest. So like we're going to like approximate, right? So, population of a town 10 years ago is 5,085 people. Well, I'm just going to say that's like 5,000, right? I don't even want to think 5,100. That even seems harder than I want to make it. So I'm just going to go right to saying, all right, well, we're going to say about 5,000 people. And same thing, my 19.51%, that's pretty close to 20%. I'm going to work with 20%. your answer choices are all off by 500, so it's not going to make a huge difference if you round it up here and round this one down. So we're good, right? So, you're basically saying, all right, well, if it was 5,000-ish people and it increased by 20%, what's a 20% increase from 5,000, right? Well, 20% of 5 is like 1/5 of 5, which is just another 1,000, right? So 20% of 5,000 is 1,000. So if I was at 5,000 and I increased by 1,000 more, I'm at 6,000 people. 5 you can do on your own. That's another ID one. 6, things doubling, you'll get there. 7, we'll do 7. With 7, it just basically says, similar to the first one we did, which of the following is always true, sometimes true, or never true, right? So the sum of a rational number and a rational number is rational. Well, if you're not sure, pick easy rational numbers to work with. So anything that can be written as a ratio as a rational number, like 2. 2 over 1, 2. Right? So plus another rational number, sure, 3, right? That equals 5, which is definitely a rational number. And if you don't introduce an irrational part to a sum, right, it's never going to be irrational. So that's always true, right? So always true. The second one, the sum of a rational number and an irrational number, so let's make the second one a root 3. Now it's irrational. Is that sum going to be irrational? Well, yeah, of course. So you can't, there's no way to get rid of that radical 3 if you're just adding two numbers together. So that's going to, same thing, make the whole thing irrational. And there's not really any way you're going to be able to get rid of it. So that's always. The third one here is the sum of a irrational number and an irrational number. So I'm going to change this 2 to root 2. Now I have irrational plus irrational. And yeah, they're not like terms. There's no way to combine them anyways. They're going to stay with radicals. So that is going to be another always irrational. All right, but now we're going to go to some multiplication ones, right? So if it's multiplication, product, right, multiplication. So rational number plus or times rational number, like 2 times 3. Yeah, that's 6, right? If you don't introduce a radical or a pi or anything like that, it's never going to get it in your answer. So that's always rational. Product of a rational and an irrational. So if we make this a root 3, now we have rational times irrational. And again, there's no way you're going to get rid of that radical. It's going to stay in there. So that's always irrational. And then the last one, irrational times irrational. So root 2 times root 3. That is root 6, which is irrational. So it works for that one. But if you could think well, wait a second. What if I did root 2 times root 2? Irrational times irrational. However, the answer is just 2 for that one, right? Root 4 if you want to think of it that way, but it's 2, and that is rational. So this last one is actually a sometimes, right? Most of the time it's irrational, but in cases like this, you can actually get back to rational as long as you're multiplying the two radicals, and it works out to be something perfect. So that's that one. So number 9, we are going to do, Sadie has a cousin, Nanette, in Germany. They both recently bought cars. They're comparing how fuel efficient the cars are. Great conversation, right? So Sadie tells Annette that her family's car gets 42 miles per gallon. So we got 42 miles per gallon, which we're going to use that. And then Annette has no idea how that compares to her family's car, but her family's car uses 6 liters per 100 kilometers. So we got 42 miles per gallon and 6 liters per 100 kilometer. You got to figure out which one's more fuel efficient. So if you noticed, you might not have noticed it when you did the practice test, but if you do the practice test in the MCAS, what you see here, right? So, if you guys didn't notice, you have basically your graphing calculator if you ever needed it. Since we mostly use Desmos in our class this year, I would always just use Desmos, and then you can create your own Desmos graph the same way. It works the same way. Just make it bigger so it doesn't look so confusing. But basically you can make a Desmos graph in there. But what's also good is what here is in the exhibits, and that basically is, you got Pythagorean theorem, you got sine, cosine, tangent for this angle here. You got a few volume formulas, you can plug them in, area formulas, special right triangle sides, all that stuff, right? But it also gives you conversions. So, I can see I had I had liters and gallons. So I'm going to write 1 liter is 264 gallons. And it also had miles and kilometers. So 1 kilometer is 0.62 miles. So, those are going to be helpful pieces of information for me, right? So I'm going to go back to my other one here. And so I had, my conversions were hold on, forgot. 1 kilometer is 0.62 miles. 1 kilometer equals 0.62 miles. And it also had 0.264 gallons was equal to 1 liter, was the other thing it had. Maybe in the other opposite order, but same thing. Now, if you're looking at Sadie has 42 miles per gallon, per 1 gallon, right? Or per gallon. And this Nanette girl had, 6 liters per 100 kilometers. Since this one had the distance on top, I'm actually just going to write the 100 kilometers per 6 liters. And just like you did in chemistry, like molarity stuff, it's kind of the same way. So I want to try and convert this to miles per gallon, or I could work the other way and convert that to kilometers per liter. But I think it's easier for me just to work with the kilometers per liter and convert it into miles per gallon. But it really is no different. So in my case, I'm going to try and get rid of liters. So I know that 1 liter is equal to 0.264 gallons. And so that way the liters get canceled out. And then, I got the other one. So 1 kilometer will cancel out the kilometers, and that's the same thing as 0.62 miles. And you could do that right on Desmos. Multiply this fraction by this fraction by this fraction. And if you do it, it comes out to be 39 miles per gallon. And all that's saying is that compared to the 42 miles per gallon, 39 miles per gallon is not quite as good. So it just means that Sadie's car is a little bit more fuel efficient. So just make sure you show your work and answer that question. Last question here, right? Just basically a proportion. You got 1 serving. It's a 16.9 ounce bottle of a sports drink. 1 serving is 8 ounces. Of 8 ounces has 50 calories, right? So how many calories are in the full 16.9 ounce bottle? So there's a few ways you can do this. You can figure out how many calories are in each ounce and then multiply it by 16.9 ounces. That's fine. That's what my last class wanted to do. I just think it's easier if you set up a proportion like 8 over 50, right? So 8, right? You can label it if you wanted to, but basically 8 ounces over 50 calories is going to equal 16.9 ounces. So that way the ounces are both on top over, some number of, I'll use X. And then I could just solve for X by cross multiplying. So you get like 50 times 16.9 is going to equal, 50 times 16.9 is going to equal 8x. So then I can just divide by 8 in the final step. I'm just doing it this way now because I don't have my calculator open. But so basic 16.9, I'll go right back to that app that I had here. So if I want to use the calculator, I'll just go right on Desmos. So I have 50 times 16.9. That's going to be 845, and then I can just do 845 divided by 8. Gives me, whoops, didn't mean to do that, equals 105.625. So that's my answer, right? So we got 105.6 calories in the full bottle, which should kind of make sense. It's a little more than twice as much, so it's a little more than twice as much for calories. Now, if a 20-ounce bottle contains 130 calories, is that consistent with this same information? With 16-ounce bottle, but it could also say the 8-ounce bottle because those are consistent with each other when we did it as a proportion. So, basically, you're setting up the same thing. You could say 8 over 50 or 16.9 out of the 100, whatever we got as the last answer. Is that the same thing? Is that going to equal 20 over 130, right? Is that the same proportion? And it's not, like if you think about it, right? So from 8 to 20, that's like doubling. So that just means if I had a 16 ounce, it should give me 100 calories. And then if I have 20 ounces, that's like another half of 8. which means another half of this should give me 125. There's other ways to figure this out, guys, if that's confusing. But like, it really should be a 20-ounce bottle. Should not have 130. It should have 125, right? And it kind of hints that it's not the same because it says, how can you explain this discrepancy? And that's up to you how you want to answer it. I think it's probably a rounding thing. Like when you see calories on the side of a sports drink, it's usually rounded to like the nearest 10 or 5. So it could just be a rounding thing. Somebody in the last class said that maybe the larger bottles have a little more sugar in them or a little more ingredient in them. Sure, right? But something that explains why it's not the same is really what you're after there. So that's it for numbers and quantity.